A transmitter may generate 100 watts of RF power. But does all 100 watts reach the receiver? Not even close. Along the way, electromagnetic energy is lost in conductors, dielectrics, the atmosphere, and surrounding objects. Understanding where this energy goes is one of the most important tasks in RF engineering. In previous lessons, we learned that electromagnetic waves carry energy through space and interact with conductors, dielectrics, and surrounding materials. Ideally, all transmitted energy would arrive at the receiver. In reality, however, this never happens. Every practical RF system experiences losses. Transmission lines absorb energy, dielectric materials dissipate power, antennas are not perfectly efficient, and the propagation environment continuously removes energy from the signal. As a result, the received signal is always weaker than the transmitted signal. This creates a major engineering challenge. If energy is constantly disappearing from the signal, where does it actually go? Understanding the answer is essential for predicting communication range, system efficiency, and overall RF performance. Loss mechanisms are physical processes that remove energy from an electromagnetic wave and convert it into other forms, typically heat. Whenever RF energy interacts with real materials, some of that energy is dissipated. Conductors have finite resistance, dielectric materials are not perfect insulators, and propagation environments contain objects that absorb or scatter electromagnetic energy. Losses can occur inside RF components, transmission lines, antennas, or during free space propagation. Engineers typically classify losses into several categories, including conductor losses, dielectric losses, radiation losses, mismatch losses, and propagation losses. Together, these determine the overall efficiency of an RF system. Intuitively, loss mechanisms can be compared to friction in a mechanical system. A moving object gradually loses energy due to friction and air resistance. Similarly, an electromagnetic wave gradually loses energy as it interacts with its environment. Physically, consider an RF signal traveling through a coaxial cable. Part of the energy is dissipated because current flowing through the conductors encounters resistance. At the same time, the dielectric material inside the cable absorbs a small amount of energy due to molecular polarization effects. Both processes convert RF energy into heat. Mathematically, losses reduce the amplitude and power of a propagating signal. The greater the loss, the faster signal power decreases with distance. Engineers use attenuation measurements to quantify how much energy is removed from the wave as it travels through a system. Loss mechanisms influence every RF design decision. Engineers selecting transmission lines, PCB substrates, antennas, filters, amplifiers, and connectors must evaluate how much power will be lost during operation. For example, microwave systems often use low-loss dielectric materials because even small losses become significant at high frequencies. Antenna designers strive to maximize radiation efficiency so that more input power is converted into useful electromagnetic energy. Communication engineers calculate link budgets to ensure sufficient signal strength reaches the receiver. At the system level, losses affect communication range, battery life, transmitter power requirements, thermal management, receiver sensitivity, and overall network performance. Managing losses is therefore one of the core objectives of RF engineering. Loss mechanisms explain why real RF systems never achieve perfect efficiency. Every practical communication link loses some energy, and understanding those losses allows engineers to design systems that remain reliable despite these limitations. A common misconception is that increasing transmitter power can solve every communication problem. While additional power can help, excessive losses often indicate deeper design issues involving materials, propagation conditions, or system architecture. Reducing losses is frequently more effective than simply increasing power. As electromagnetic waves move away from an antenna, another important distinction emerges. The behavior of fields close to the antenna is very different from the behavior farther away. In the next lesson, we will explore near field versus far field, and discover how electromagnetic fields change with distance from the source. In this lesson, we learned that loss mechanisms remove energy from electromagnetic waves and convert it into other forms, primarily heat. We also saw how conductor losses, dielectric losses, propagation losses, and mismatch losses affect RF system efficiency and communication performance. In the next lesson, we will explore near-field versus far-field and discover how electromagnetic field behavior changes as we move away from an antenna. If you found this useful, like the video, subscribe, and follow for the next lesson.